Hello everybody, it is Emir from University of North Carolina at Chapel Hill. Today I'm going to talk about how we try to use the PETALUTE to bridge the gap between preclinical, clinical, and metabolomics, MRI, and MRI approaches. Before getting into the technical details, I would like to show an animation that actually summarizes our acquisition trajectory. It is consisting of lots of petals and traveling around the case space that we need to acquire. The reason we call it novel and fast and flexible in the same title is because acquisition trajectory makes us acquire different contrast, different modalities in one binaries that has been implemented for the Bruker. So you can acquire MRI, you can acquire spectroscopy, you can even acquire single voxel spectroscopy if you turn off the gradients. Before getting through the details, I would like to introduce my collaborators. So I would like to highlight one more time that this is a group of people who works on the same topics and helping each other. So in other words, this is a community effort. We all know that MRI is consisting of hydrogen atoms that are attached to the water. And also, if we come up with an idea that get rid of the water molecules, we can see the other molecules, like spectroscopic acquisition, NAA, creatine, choline. Each individual metabolite has significantly related to certain markers. So it is important to know that having a signal attached to the hydrogen atoms are important. Hydrogen atoms not only attach to our focus of interest, such as water or metabolites that we are studying in the brain. Sometimes they are attached to the background signals. So this background signal, depending on where the organ is, could be useful or sometimes unwanted signals for our processing. So for the muscle, for example, we are desperately looking for to get the lipid metabolites, and whereas in the brain it is causing a problem. As illustrated here, when we look at trajectories across different metabolites, what we found is macromolecules are highly correlated with the aging, developing brain. So it is important to figure out a method that should deal with the background signal. What we know from the literature is usually these background signals has very short T2s, T2 stars. So that makes it the relaxation times decay constant is very fast in the magnetic field. So in order to achieve this and try to get important information, fast decaying signals, conventional acquisition methods are not sensitive or cannot detect this ultra short T2 star decaying signals. So these signals can be found in myelin sheaths, lung tissue, cortical bones, and tendons. Ultra-short echo time or zero echo time methods reduce the acquisition delay near to the zero, allowing for imaging ultra-short T2 components. Illustrated here, the conventional acquisitions acquire the data in late period of the T2 star decaying. However, when you switch the paradigm to the zero echo time or ultra-short echo time, you can capture the most of the signal that we are losing with the conventional methods. Illustrated here from our myelin imaging method, when we subtract the first echo and second echo, we start to see the signal decay that is originating from the white matter and most likely the myelin tissue. In order to deal with this problem, we developed a case-space trajectory that is originating from rosette. Conventional rosette illustrated here, we try to change it, try to make it compatible with clinical scanner without hurting the gradients, and at the same time boosting the signal-to-noise ratio. And that we tailor it to the PETALUTE acquisition. So this acquisition trajectory has recently awarded by MRI Reproducibility Challenge, and at the same time Bruker MRI Award 2024. As illustrated here, the modified rosette has significantly sampling the center case space, and that allows us to bring back the signal, and this is how we change the acquisition trajectories for ultra short echo time. During the COVID time, with my student Xin Shan, he is right now at UCSF, we decided to use the PETALUTE to solve this problem. And we initially started with the Rosette formula. Basically, using this formula, one can acquire a radial acquisition. As illustrated here, this is the relationship between W2 and W1. And simply manipulating this, you can acquire spiral as well. So, in theory, the PETALUTE binaries can be used for radial acquisition and at the same time spiral acquisition. However, in this study, we try to change it. In a way, W2 equals to W1. That allows us to center out, and at the same time, we can bring it back with this formula. So that then we start to change the angular orientation of this petal and separating two different acquisition from the middle of the petal. So the red and the green ones are illustrating the first echo and the second echo. So you can generate two images during one acquisition. At the same time, you can boost your spectral bandwidth for spectroscopic acquisition, as we are implying for 7 Tesla, 9.4 Tesla, as you will see shortly in this presentation. Basically, these petals can be tailored to different shapes, and that's the reason we call it PETALUTE. I would like to highlight this because we developed this method during the COVID interval. So we didn't have access to scanners. We used simulations, and these simulations help us to get this sequence working immediately. Pay attention to the dates. So December 22nd, when we finished the simulation, and January 10th, when we acquired the first lung imaging. Okay, so we will continue with the in vivo applications. In particularly in this presentation, I will try to focus mostly ultra high field. The first application will be the magnetization transfer 7 Tesla. In this study, we approach subjects and recruit them 3 times and to see how magnetization transfer based myelin imaging methodology reproducible using Rosette trajectories. Following our retest reproducibility measurement, we look at the subcortical areas and cortical areas to see how reproducible myelin content measurements using magnetization transfer approach with PETALUTE. As illustrated here, our ICC values overall at the higher end of the expected values. So this demonstrates that these measurements with the PETALUTE are reproducible. Following our success using phosphorus spectroscopic imaging with the reproducibility challenge in 2023, we decided to use the phosphorus spectroscopic imaging of the PETALUTE at the 7 Tesla. With 4 times acceleration, which resulting in total acquisition of time 6 minutes, we successfully acquired phosphorus spectra from whole brain, as illustrated here. So, following this success, we try to implement the PETALUTE for sub-millimeter fMRI acquisition at the 7 Tesla. As illustrated below, we again subdivide the petals into 2 pieces, first echo and the second echo, and this generates 2 different contrast mechanisms for fMRI signals. Both of them are related to the functional activity, but origins are totally different. We also compare our dual echo Rosette acquisition with multiband EPI. As illustrated here, dual echo Rosette or PETALUTE acquisitions are immune to the B0 inhomogeneity as compared to the multiband EPI. So what I phrase it is, you can get an MP-range contrast and fMRI signal with the PETALUTE without having any issue with the B0 inhomogeneity. Also, success of the PETALUTE push us to try more complicated organs like the lung. As illustrated, we acquire 5 minutes PETALUTE acquisition and free breathing and with retrospective motion correction. As illustrated here, we acquire very high resolution lung images, and this allows us to monitor the motion intervals easily using IMOCO reconstruction. in summary, we successfully acquire many applications at the human scanners. And this is because of the acquisition is reducing the gradient, reducing the slope rate, starts with the center of K-space, and no need to single point images and dual echo without any delay between echoes. But we would like to also challenge this for preclinical acquisitions. This translation helps us to get the MRI Brooker Award in 2024 with the PETALUTE acquisition. Again, we challenged the acquisition with X nuclei because of the lack of signal-to-noise ratio and desperately looking for ultra-short echo time delays. So this allows us to map the phosphorus signals in the abdominal part of the mice, as illustrated in this slide. Then we challenge it for GABA imaging. In other words, neurotransmitter imaging. According to this acquisition, at 9.4 Tesla, using 4-channel mouse brain coil, with a semi-laser localization, we successfully acquire spectra that is indicating the GABA signal, as illustrated here. We also tested our acquisition with semi-laser spectroscopic imaging with an echo time 36 milliseconds at 9.4 Tesla with single-channel mouse brain coil. Illustrated here is the water-suppressed signals that is originating from the semi-laser localization. The red lines indicate the individual spectra, and as illustrated, these are the corresponding spectra from the red line illustrated here. So as can be seen, the water suppression is very efficient and very well resolved peaks at 9.4 Tesla. As we did at the 7 Tesla human scanner with the magnetization transfer, we also conducted magnetization transfer ratio using PETALUTE acquisition at 9.4 Tesla. Here you can see the MTR maps that is achieved by UTE, PETALUTE, and PETALUTE with magnetization transfer acquisition. So as illustrated here, MTRs are significantly higher in the regions of where we are expecting to be the white matter regions. At the same time, you can use this approach to direct myelin imaging. In this experiment, what we did is the excised brain gone through the same procedures, and with the complex fitting, we identified 1.7 ppm, and the same slice has gone through the lipidomics, and we look at which lipid components are clearly explaining the direct myelin imaging findings that is originating from the PETALUTE. Finally, in order to be parallel with the 7 Tesla approaches we have been used for human scanners, we would like to try the fMRI acquisition at the 9.4 Tesla. Single slice acquisition, as illustrated here, we were successfully get the resting state fMRI with using first echo and the second echo illustrated in this presentation. What is next? I would like to highlight my colleagues at the workshop to visit Dr. Lijing Shins and her student Jiwei Huang, and for their presentation about rosette spectroscopic imaging for whole brain metabolite map at the 7 Tesla, and we also explored the acceleration potential of this acquisition and at the same time reproducibility.